Chapter 19 is not a new technique. It's laying the foundation for the new technique that we're about to learn in Chapter 20. So in Chapter 15, we learned how to solve homogeneous equations where we had constant coefficients. Now we're going to be turning our attention to solving similar things that are non-homogeneous. In Chapter 17, we solved higher order homogeneous equations. Now we're going to have similar looking non-homogeneous equations. Now if you recall, when we're dealing with homogeneous equations, if we had y1 and y2, which were both independently solutions to the equation, then we know that another solution would be the linear combination of those two. But that is not the case with non-homogeneous equations. Now in your textbook there is a nice, detailed, although lengthy explanation for why this works the way it works, although it is not a proof of that. But we're going to be solving non-homogeneous equations. We can solve the homogeneous equation. That's what we learned in earlier chapters. We're going to call that solution y sub h. And somehow we need to come up with a solution to the non-homogeneous equation. Now that's what we're going to be doing in the next chapter. For right now, they're going to be suggesting solutions that we need to check. However, the two together constitutes what we call the general solution. Now, taking a look at this second order non-homogeneous equation, we might just guess, since the right hand side of this has an e to the 3x in it, that perhaps e to the 3x is a solution. Now we can actually check to see if that's the case by doing the derivatives, substituting them in, and see does it work. Well, of course it does, probably because I picked it so that it would. However, we will find the homogeneous solution like in an earlier chapter. We're going to find the characteristic equation, r squared minus 4 equals 0, solve that, get the two distinct real roots, 2 and negative 2, which suggests to us this solution. So now our general solution is nothing more than these two combined together. Now I'll just finish this out with a little observation that simply is, so what should this be if y equals 3 to the e to the 3x is indeed going to be a solution? So here's what we can do. We can do the derivative, plug that in, and see what it comes out to be. Well, it comes out to be 10 e to the 3x. So if this were y double prime plus y equals 10 e to the 3x, then e to the 3x would be a solution. So we'll kind of use that information in some of the problems in this chapter, and then in the next chapter see some better ideas for coming up with solutions.